So welcome to this lesson on Regula Falsi Method numerical analysis, and this is a very useful method in finding the root of an equation. Now, what are numerical methods? They provide techniques to find approximate solutions to problems, and they involve sequential steps, so they are useful in computer programming. Now, equations involving algebraic terms such as x, x cubed, root x, etc. are called algebraic equations, and equations involving e raised to x, log x, sin x, etc. are called transcendental equations. So in today's lesson we will be learning how to solve equations in both algebraic and transcendental forms. Now, if fx equal to 0 is a real valued continuous function, and if fa less than 0, f of b greater than 0, then there always exists at least one real root in the interval ab. So one iterative method is the Regula Falsi method or method of false position. So it's either called Regula Falsi method or method of false position. So it says that let fx equal to 0 possess only one real root in the open interval ab, and let fa be less than 0, fb be greater than 0, then x equal to a fb minus b fa by fb minus fa. So this is the approximation of the root. So we will start with problems without wasting too much time. Use Regula Falsi method to find the real root of x cubed minus 2x minus 5 equal to 0, correct to 3 decimal places. So we start with let fx equal to x cubed minus 2x minus 5. Now f of 0 will be minus 5, and f of 1 is minus 6, f of 2 is minus 1, they are all less than 0, but f of 3 is 16, which is greater than 0. So f of 2 less than 0, f of 3 greater than 0. So the root lies in the interval 2 to 3. Now supposing I take f of 2.1 and I substitute f of 2.1 here, you get it as this will be greater than 0. And f of 2 is less than 0, so the root lies between 2 and 2.1. Now we take f of a as 2 and b as 2.1 because f of 2 is negative. So f of a is minus 1, f of 2.1 is 0.061 when you substitute. So x1 in this case will be a fb minus b fa by fb minus fa. Substituting for the values of a and fa and fb and b, you get x1 as 2.0942. So we have found x1. Now we calculate f of x1, substituting in the equation for fx. So you get minus 0.00392, which is less than 0. So the root lies between 2.0942 and 2.1. Why? Because f of 2.0942 is less than 0 and f of 2.1 is greater than 0. So this is how you approximate. Now you take a as 2.0942 and b as 2.1, and again we calculate x2 as a f of b minus b f a by fb minus fa. So this is the second approximation. And you get x2 as 2.09455. Now x2 is very close to x1, where x1 is 2.0942. So we take the root as 2.095. We round it. The next question, use Regula Falsi method to solve x raised to 4 equal to 12. So again we assume that fx equal to x raised to 4 minus 12. Now this is an algebraic expression. So f of 0 will be less than 0, f of 1 is minus 11 less than 0, f of 2 is 4 which is greater than 0, so a root lies between 1 and 2. Why? Because f of 1 less than 0, f of 2 greater than 0. So we calculate f of 1.1 now. This is less than 0. You can check using your calculator. F of 1.2 is less than 0. F of 1.3 is less than 0. So we are keeping on checking to find a value which is greater than 0. F of 1.4 is less than 0. F of 1.5 is less than 0. So we are just using trial and error and checking. F of 1.6 is less than 0, f of 1.7 is less than 0, so we keep on approximating. F of 1.8 is less than 0 and f of 1.9 is greater than 0. So the root lies between 1.8 and 1.9. Why is that? Because f of 1.8 less than 0, f of 1.9 greater than 0. So we take A as 1.8, B as 1.9, and we take our first approximation x1 equal to AFB minus BFA by FB minus FA. So this is your first approximation, and x1 will be 1.8593, and f of x1 when you substitute will be minus 0.0492, which is negative. So we have calculated x1 and f of x1. So because f of x1 is less than 0 and f of 1.9 greater than 0, the root will lie between 1.8593 and 1.9. Then again we put A as 1.8593 and B as 1.9. Why? Because f of A less than 0, f of B greater than 0. And then we take our next approximation x2 as AFB minus BFA by FB minus FA. So you get x2 as 1.8612 and f of x2 is less than 0. So what have we done? We have calculated x2 and f of x2. So a root lies between 1.8612 and 1.9. Again you put A as 1.8612, B as 1.9. So remember that f of A is less than 0, f of B greater than 0. And we calculate a third approximation x3 as AFB minus BFA by FB minus FA. So you get x3 as 1.861, and this is very close to the third root, which is 1.861. So we can say that the answer is 1.861, or the fourth root of 12 is 1.861, because we have to basically calculate x raised to 4 equal to 12. Coming back to the question. Okay, the next question and the final question will be, use Regula Falsi method to solve tan x plus tan hyperbolic x equal to 0 given that a root lies between 2 and 3. Show 3 approximations. So here you are given that the root lies between 2 and 3. So let fx be tan x plus tan hyperbolic x. So f of 2 is minus 1.221, which is less than 0. You can calculate this using your calculator. F of 3 is 0.8525, which is greater than 0. So let A is 2 and B is 3. The root has to lie between a negative and a positive value. Note that is f of A less than 0, f of B greater than 0. So we calculate our first approximation x1 is AFB minus BFA by FB minus FA. Substituting you get it as 2.59, and f of x1 is 0.3735, which is greater than 0. So what is f of x1? It is positive. So the root will lie between 2 and 2.59. So let A is 2, B is 2.59. We calculate a second approximation x2, which is again AFB minus BFA by FB minus FA. So note that everywhere we are using the same formula. So substituting you get x2 as 2.4518, and f of x2 will be 0.1603, which is positive. So now where will your root lie? F of 2 is less than 0. So let A is 2 and B is 2.4518. Again we calculate a third approximation x3 is AFB minus BFA by FB minus FA. So we keep repeating this and we get x3 as 2.3994, and we only have to calculate 3 approximations because that's what is asked in the question. So we say that the third approximation is 2.3994. So we have just covered a few problems on how to use the Regula Falsi method in numerical analysis. So thank you and stay tuned in for the next session.